Okay, good morning, folks. Welcome back for the second discussion of the photoelectric effect, which will give us a nice bridge into scattering theory, which will be the main subject of next week. Before we dive in for physics for the day, there's one thing that I wanted to discuss with you, so let me share screen momentarily. That is that I have finally succeeded in writing the solutions and verifying homework 7, so I finally got this one posted. I had intended to get this posted to you last Friday, and that didn't happen. It took a lot longer than I expected to hone and fine-tune these problems the way that I wanted them to. So here is what homework 7 looks like. It would have been nice to have had it due this week, but that's obviously impossible, so I pushed back the due date to next Friday. The homework is 25 points, so that is 5 points worth of conceptual questions, these two. And then 2 problems which are really the same problem, but in 2 parts. The calculation is not particularly complicated. It's just a little bit of algebra here, easier than several homework assignments you've done recently. But there's some conceptual issues that I'm trying to walk you through. So the conceptual questions associated with the Stark and the Zeeman effect. This is atoms and external fields. The first question is about the dependence of different states of hydrogen on the electric field E, whether they depend linearly or quadratically. Remember, this came up in the context of whether they had a correction at first order in perturbation theory. First order meant that they would depend at first order on the electric field, that is linearly. Or if the first order correction vanished, then they would only depend at second order or quadratically on the electric field. So this is very similar to the discussion that we had in class about the n=2 states, where the states were degenerate, and the Stark effect potentially could vanish in any given one of the states, but for certain linear combinations, it might not. So this is the same kind of question now applied to a specific set of states in the n=3 shell, the 3s, 3p, and 3d states, specifically the ones with Lz=0. So when you consider what the effect of the Stark Hamiltonian is, this EEC operator, you need to figure out how these states can mix with each other according to the selection rules associated with this operator. And then based on those selection rules, you can figure out how these states can mix. So the question is, which states will depend at first order on the electric field? How many of them are there? And which states and how many will depend quadratically on the electric field based on the possible mixings of those 3 levels? So this is really about what kind of mixings are allowed by the selection rules. You do not need to actually calculate any of those matrix elements. So if you find yourself setting up a complicated integral, you've probably made it more complicated than it needs to be. The second part is again about selection rules associated with these kind of operators. We talked extensively about the selection rules associated with a vector operator, something like C, which is a component of the vector R. So if I give you a more complicated electric field, something like x I hat minus y j hat, this operator, so this electric field, when you put it together with the position operator, acts like a rank 2 tensor, which follows a different set of selection rules. So I'm asking you to figure out what those selection rules are going to be. For your reference, I'm giving you explicitly the decomposition of a rank 2 tensor in terms of its L and M components. So we talked in class about how selection rules arise because of conservation of angular momentum. So if you know what this operator is, then you can decompose it into contributions coming from +2, +1, 0, -1, and -2 components of a rank 2 tensor. And so based on the amount of angular momentum which is being carried in these operators and therefore in this operator, you can figure out what the selection rules are. Again, you should not need to actually compute any matrix elements for this. For the problems, the real one problem which is on the homework assignment is about revisiting the Zeeman effect, including the fine structure of hydrogen. So in class, we did the Zeeman effect for the Coulomb energy levels, which only included the Coulomb attraction between the electron and the proton. It did not include L.S fine structure. It did not include hyperfine structure. So this question is about how to treat the Zeeman effect with the fine structure. So I remind you what the Zeeman Hamiltonian is. It's L plus 2s, the factor of 2 coming from the g factor of the electron spin. And so the first two questions are really just numerical estimates. I ask you to estimate the strength of the magnetic field when each approximation is reasonable. How strong does the magnetic field need to be for the case we considered in class, when the magnetic field is a small correction to the Coulomb energies, but it's much bigger than the fine structure, which can be ignored. So you can estimate the range of the magnetic fields. And then similarly, you can estimate the range of the magnetic fields appropriate for this problem, where the Zeeman shift is a small perturbation to the fine structure energies, but it's still big enough that you can ignore the hyperfine structure. So these are just some numerical estimates, not really much involved there. The heart of the problem is calculating the Zeeman shift in the 2s1/2, 2p1/2, and 2p3/2 states. So the exercise here is you have this Hamiltonian, which knows about L and S separately. This Hamiltonian is diagonal in the product basis. The difference is that in the fine structure levels, the eigenstates are the eigenstates of total angular momentum J. So in order to evaluate the shift from this Hamiltonian, you need to convert from the total J states back to the product basis, L and S. So you will use the Clebsch-Gordon coefficients. So I have posted that link here for your convenience to refer to the tables. That's all the exercise is. There are a number of different JZ states. And here you have J equals 1/2 for the 2S, J equals 1/2 for the 2P, and J equals 3/2. So for each of those states, you have various values of JC, and you will calculate them all. So this is the only one that involves a significant amount of quantum mechanics. This is really the hardest part, if there's a hard part at all on this homework assignment. So this is sort of answering the question of the Zeeman effect in the fine structure levels by brute force, by direct calculation. The second part is an analysis about why the structure is what it is. So you don't have to redo the calculation. This is a reinterpretation of the same thing based on rotational symmetry. We talked a little bit about operators carrying angular momentum, which is embedded in the Wigner-Eckart theorem. That's part of why we ended up with selection rules like this. This helps explore a second piece of that, which is to say that when you do this calculation, the different values of JZ are related to each other. You get one set of relations for J equals 1/2, one set of relations for J equals 3/2, but the different JC values are all connected by rotational symmetry. So this is the form of the Wigner-Eckart theorem. When you take this Hamiltonian, this one, it depends on a vector operator. And since it depends on a vector operator, that operator carries L equals 1 and M equals 0 units of angular momentum. So part of what the Wigner-Eckart theorem says is that these matrix elements are only allowed to depend on JZ in a very specific way. That they can only depend on JZ through the Clebsch-Gordon coefficients, the ones you look up in the table. So the exercise here is to analyze and understand how they depend on JZ. These constants, C1, C2, C3, are called the reduced matrix elements of this Hamiltonian. And you can calculate them just once. Calculating these for one value of JZ is enough to determine them for all values of JZ. And you can do the same thing for any vector operator, including JZ itself, and you get a different set of reduced matrix elements. So the exercise here is to reanalyze the same result you had before in this context. So part A is just take these operators and evaluate them. Evaluate the constants C1, C2, and C3 by plugging in one particular state. You don't have to do it for all JZ. You can just do it for, say, the top state of each ladder. That, if you plug in your answer from the previous problem for the left-hand side, you look up the Clebsch-Gordon here, then that will let you determine what the coefficient is. Once you've got all three values of the coefficients, you know the answer for any JZ. Then you can do the same thing for the matrix element of JZ itself. That's even simpler. Once you know both, the C constants and the D constants, you can use this to plug back in, essentially solve this equation for the Clebsch-Gordon coefficient. That's what's going on here in part C. If you solve for the Clebsch-Gordon coefficient, you write this Clebsch-Gordon coefficient in terms of JZ and this constant D1 you calculate. And then you plug it back into the first equation. So you explicitly show that these matrix elements are proportional to JZ because of this rotational symmetry. So this should reproduce the answer that you got here by brute force by calculating all of the matrix elements by hand. This tells you you could have just calculated one matrix element for each of the ladders, and then use the symmetry to know that they have to depend on JZ. And then the last part asks you to generalize the logic to say, what if we were thinking about the hyperfine levels where it's not JZ, but something else? And ask you, how should these things depend on the point? So not a lot of complicated math, but you need to take your time and work through it to make sure you understand what's going on. Any questions about homework 7? So like I said, this one I have set due next Friday. That puts me a bit behind in terms of assigning homework to you guys. So I am planning on writing homework 8 based on the scattering theory that we've started discussing already and will continue today. I will try to post that tomorrow, post that by Friday. And again, I think I will have that nominally due next Friday, but I will make it a short assignment. I will have it only be like 10 points, 1 problem worth, maybe 2 conceptual questions, 2 elementary scattering cross-section calculations. So there won't be any long analysis problems on that. That's sort of what I'm thinking. Do you guys have any questions, concerns, or comments for me? Okay, if not, then let's pick up where we left off on Monday with the photoelectric effect. So the photoelectric effect we were discussing, of course, involves an incoming electromagnetic plane wave. We have the electric field E, the magnetic field B. This plane wave is really a distribution of photons. It's a whole beam of photons, each one carrying energy, h bar omega, and momentum, h bar k, where k is the wave vector telling you the direction of propagation of the photon. And we were looking at the transition of the hydrogen atom between its ground state, 1, 0, 0, absorbing energy from the photon that then promotes it up to a free particle state. So our energy initial is that minus 13.6 electron volts, the ground state energy of hydrogen. The energy final is some P final squared over 2m free kinetic energy. And the difference from one to the other is the energy h bar omega being absorbed from the beam. So first we started off last time with a review of classical electromagnetism to remind ourselves about electromagnetic waves and what they look like. So at the end of the day, we derived that there were electromagnetic plane waves as solutions to Maxwell's equations in vacuum. And we showed that in Coulomb gauge, this is written very simply as a wave solution of the vector potential. And that wave solution of the vector potential translates into a wave solution of the E field and the B field. So in Coulomb gauge, we'll use the A field directly to calculate the perturbation. The interaction of that vector potential with the hydrogen atom was given by minimal coupling. It turns out to be of the form A dot P. When we plug this in, we had 2 terms. The cosine form, we split up into e to the I omega t and e to the minus I omega t. The piece that we're keeping explicitly is the one that comes with e to the minus I omega t. The one that we dropped was proportional to e to the plus I omega t. Remind me, why were we allowed to drop the term with e to the plus I omega t?
Because you can't lower the energy.
That's right. The plus I omega t term would have subtracted h bar omega energy. Since we start off in the ground state for this problem, that will not cause any allowed transitions for us. It would violate conservation of energy. So we only have to worry about the positive energy component of the wave, the e to the minus I omega t term. And the strategy was to plug this into Fermi's golden rule. The only subtlety here is that before we were talking about Fermi's golden rule between discrete states, and now if we're talking about a transition to a momentum state, there's an infinite number of momentum states that are allowed. So this is not like a probability and a rate, this is like a probability density and a transition rate density per unit D3 momentum. So this is a D rate D3P final. And otherwise it looks exactly like Fermi's golden rule. 2 pi over h bar, transition matrix element squared, energy conserving delta function. And the main exercise that we went through last time was evaluating that transition matrix element. And what we found after some integration was that the solution involved a whole bunch of constants, e over 2mc from the Hamiltonian, 1 over 2 pi h bar to the 3 halves, coming from the normalization of the plane wave. 1 over pi Bohr radius cubed, coming from the normalization of the hydrogen ground state. The form of the solution was vector potential dot P initial. And the solution from doing the integrals was 8 pi Bohr radius cubed h bar squared over h bar squared plus P initial squared Bohr radius squared, everything squared. In this expression, we've introduced this variable P initial, which is defined to be the measured momentum P final minus the h bar k momentum, which has been added. So this is a natural variable to express the solution in terms. Okay, so we've done the hard work of evaluating the transition amplitude. The last step is to take that and plug it back into Fermi's golden rule, and we will now calculate the transition rate. Any questions before we dive into that part? Okay. All right, so plugging back in, we have transition rate density per unit momentum final is equal to 2 pi h bar. And now I'm going to take this thing and I'm going to take its absolute value squared. So I get a whole slew of constants in front. I have E over 2mc squared. I have 1 over 2 pi h bar cubed. I have 1 over pi Bohr radius cubed. I now have the magnitude A naught dot P initial squared. And I have even more constants. 8 pi Bohr radius cubed, which gets squared. And I have h bar squared over h bar squared plus P initial squared Bohr radius squared to the 4th power times the last thing was energy conserving delta function. Final minus the initial minus h bar omega. All right, so I clean up the constants a little bit and I end up with 4 Bohr radius cubed h bar squared, pull the h bar squared over, e squared over pi m squared c squared a naught dot the initial squared h bar squared plus p initial squared or radius squared h bar squared to the 4th. I think if I pull the h bar squared there, then I need a 1 over h bar to the 4th. Okay, so the form for the differential rates, it has 2 ingredients to it. So one of these things is just an overall constant. This piece tells me the direction. This contains the vector information about where this thing is likely to go. So the directional information associated with the knockout process, this is A naught dot P final minus H bar K squared. So this is telling me what direction the photoelectric effect tends to knock out the electron in. It likes to orient the direction of P final with relation to A naught. I think the easiest way to understand this is to recall that in Coulomb gauge, this vector potential was proportional to the electric field. So this is really saying the electric field of the incoming plane wave is going to kick out that electron in that direction. So in this picture, if the electric field is going vertically, then whichever direction it happens to be here, the electric field is going to knock out the electron along the y-axis. It's going to want to come out aligned vertically. The other thing is that it contains a scalar dependence down here. This tells you how fast the rate dies off for high momentum electrons. And I still did not write the energy conserving delta function. Delta of T final minus the initial minus h bar omega. So now let's handle this delta function. The energy conserving delta function tells us what allowed momentum the final state electron can have. So we said E initial is the ground state energy of hydrogen. That's that minus 13.6 electron volts. E final is related to the momentum that the electron is allowed to have when it leaves. This is P final squared over 2m. So this energy conserving delta function is really a constraint on which values of P final I can have. So this is delta of P final squared over 2m minus E initial minus h bar omega. So this rate is something which is differential in all three components, x, y, and z. Or equivalently, this is differential in the spherical component. So this is differential in the magnitude P final with the measure P final squared. It is differential in the angle theta with the measure sine theta from spherical coordinates. And it's differential in d phi. So in terms of spherical coordinates, radius, polar angle, azimuthal angle, this delta function only imposes a constraint on the magnitude. It doesn't have anything to do with the direction. Magnitude P final, not direction. So let's translate this delta function into a delta function of the magnitude P final instead of this energy. Remember the properties of delta functions, that if I have delta of f of x, that this is 1 over the absolute value of the derivative, delta of the zeros of x. So let me write it like this. So here in this case, I have a delta function of P final. So if I write this as a delta function of P final minus the thing that makes it 0, that is square root 2m P initial plus h bar omega. In front of this delta function, I have a prefactor, which is 1 over the derivative with respect to P final. The derivative with respect to P final is going to give me P final over m. So 1 over that is m over P final. So I get a prefactor from the change of variables, and now my delta function is explicitly going to set this P final equal to something. So let's take this expression for our differential rate and convert it to spherical coordinates. So we said differential rate per unit three-dimensional momentum volume element is dr over dpf, d theta, d phi, with the spherical volume element that goes with it, which is 1 over P final squared sine theta. I don't care about the angular distribution in terms of this delta function. This only has something to do with the magnitude P final. So another way to write this is to talk about the solid angle. D omega is defined to be d theta sine theta d phi. So this just tells you the angular direction that it's going in spherical coordinates. So another way to write this differential is to say that this is dr dp final d omega times 1 over P final squared. So what I'd like to do is I'd like to take this differential rate and integrate over the delta function. The rate is 0 unless the magnitude of the momentum is equal to what it must be by energy conservation. But the direction is controlled entirely by the quantum mechanical calculation. So let's take this and integrate over the magnitude Pf. Using the delta function. So when I do that, I'm going to integrate out this dp final, and I'm going to be left with the rate per unit solid angle. So differential amount of rate per unit solid angle is defined to be is equal to integrating over all p final, differential rate per unit p final per unit solid angle. Strictly speaking, this is an integral from 0 to infinity. And this thing is just a spherical change of variables, dp final from 0 to infinity times dr d3 pf times the spherical volume element, 1 over p final squared. So I'm just going to take the expression before, and I'm going to divide by this factor, and I'm going to integrate it. So what we had before was differential rates per unit three-dimensional momentum was 4e squared Bohr radius cubed over pi mc squared h bar to the fourth. A dot the initial squared h bar squared over h bar squared plus initial squared or radius squared to the fourth. And then from the delta function, I have 1 over p final I think I put my factor here backwards. 1 over p final delta of p final minus square root 2m p initial plus h bar omega. Yeah, sorry, I put my PF in the wrong place here. Dr d3 PF is 1 over PF squared dr d omega. So dr d omega is PF squared times dr d3 PF. That's better. So I have 1 over PF here. I'm going to multiply by PF squared. That's going to cancel this denominator and give me a factor upstairs. And then I'll integrate over PF, and I'll pick up the delta function. So after doing this integration, I get dr d omega, just the directional information, is 4e squared Bohr radius cubed over pi mc squared, one factor of p final now. A naught dot p initial squared, h bar squared over h bar squared plus p initial squared or radius squared to the fourth. All right, so this is basically the final answer for the transition rate density. So now you sort of see what ultimately happens to the energy conserving delta function from Fermi's golden rule. When you have a transition rate density where you've got a whole range of allowed states, you end up integrating over the delta function. And you're left with transition rate density with one less dimension, just the angular information. That tells you about the angular distribution that comes out from the calculation. So the calculation has several interesting pieces to it. The magnitude is controlled by this PF and this 1 over 1 plus PI squared to the fourth. The direction information is controlled mostly here in the numerator, A dot PI squared. It's a little bit complicated here to disentangle because we have several different variables. We have P initial, which was P final minus H bar K. And the magnitude of P final was square root 2m E initial plus H bar omega. So if I know my initial conditions, I know the initial energy, I know how much energy the photon added, I know how much momentum the photon added, then all of these things are completely determined. But if I wanted to plug all of this back in terms of sine theta, cosine theta for the direction of PF, it would be a bit complicated. So in order for us to study the properties of this solution, it's helpful to take a simplifying limit of the general answer we derive. Okay. To see the structure of the answer, consider the low energy limits. So the electromagnetic wave that's coming in can have any frequency that we choose it to. This could be an X-ray that's delivering so much energy that it kicks the electron out of the hydrogen atom and gives it tons of kinetic energy. Or we could send in a lower energy photon, which has just enough energy to ionize it and not give it huge amounts of kinetic energy afterwards. So let's assume that the energy of the photon, h bar omega, is comparable to, it's on the order of the ground state energy E initial. It doesn't have to be equal to it, but it's on that same order, right? If this one is 10 or so electron volts, then this is not 1,000 electron volts. So if that's the case, if the energy is something on that order, then we can figure out what the photon momentum is. The photon momentum is h bar k. And for the photon, we had omega is k over c, I believe. K is omega over c. H bar k is h bar omega over c. So if my photon energy is something which is on the order of the ground state energy E squared over Bohr radius times c, then the photon momentum that goes along with it is initial, yes. So this one was the one that ends up being E squared over Bohr radius c, and the energy was, okay, I've got to double check this factor. So the point that comes out of this is that this is the typical momentum of the photon that has energy comparable to the ground state. This is much less than the momentum that the electron already had inside the hydrogen atom. So the initial momentum that it has already inside the hydrogen atom is something which is on the order of h bar divided by the Bohr radius, coming from confinement, coming from the uncertainty principle. So initially, the electron is confined at a very short distance, so it has a very large momentum, much larger than the amount of momentum the photon is giving. So if I compare that ratio, momentum of the photon divided by momentum of the electron originally, then what I end up with is E squared over h bar c. And this is of order alpha E. So, okay, I botched what this factor was, but the point here is that if you consider the case when the photon energy is comparable to the energy necessary to ionize the atom, then its momentum is very small. It's parametrically of order alpha EN. So this is a way of saying in this limit, P final is approximately equal to P initial. I can neglect H bar K. And that will simplify my formulas a little bit. Everything will just depend on P final and not P initial. So I think what I'll do is I'll just take this formula and everywhere I have PF or PI, I'm going to replace it by PF. Okay, and now it's easy to plug in and see what the angular dependence is. If the direction of A naught is, let's say, along the z-axis, say, this, of course, means that the electric field is also along the z-axis. And the form of this numerator, dr d omega is proportional to a naught dot p final squared, and this is just proportional to cosine squared theta. So this goes back to my picture of that oscillating electric field. If the electric field is oscillating up and down, so now I've chosen this to be the z-axis, then what I find is that when this photon hits the hydrogen atom, the distribution of electrons that wants to come out of it is proportional to cosine squared theta. So this is a maximum when theta is equal to 0 along the positive z-axis. It's also a maximum when it's along the negative z-axis. So the typical distribution of electrons that you see coming out from the photoelectric effect in the low energy limit is basically just aligned with the electric field, and it kicks out the electron with whatever initial momentum that it had. So the amount of momentum h bar k being added by the photon was small and neglected here if it has just enough energy to ionize it. And all you do is you pick out the direction of the electric field, and you just give the electrons that were zipping back and forth enough energy to become free. So they pop out with essentially the original momentum that they had in an orientation aligned with the electric field. This is a little bit counterintuitive because it's not pointing along the direction of the photon momentum. This is because of the low energy approximation. If instead we sent in X-rays and we took the momentum to be dominated by the photon momentum, then we would instead find the opposite case, that most of the momentum comes from the photon and most of the electrons come out going forward. Okay, that is the physics of this answer. Any questions about the transition rate that we've derived? Sorry for botching the estimate here. I can go back and fix that. Okay, the next thing to discuss is a translation from this answer to something more universal, which is called a cross-section. So one thing to point out is that the rate that we've derived here is a combination of two different factors. It's a combination of properties of the wave and properties of the quantum mechanical system. Combination of properties of the beam and of the system. You might call it the targets. So for instance, one thing that we see is that this answer is proportional to the intensity of the wave. It's proportional to the magnitude of the vector potential squared. dr d omega is proportional to a naught squared. And since a naught is itself proportional to the electric field, this is proportional to the electric field squared. And this is simply the intensity. So if you do an experiment with one intensity, I do an experiment at a different intensity, we cannot directly compare our answers because we had different beam setups. It would be more advantageous if we can divide out the properties of the beam and get something which is just a property of the target. So one way to interpret this is to think about what's coming in this incoming plane wave. So the incoming electromagnetic wave. So we said it looks like this oscillating E and B field. Moving in a direction K. Another way to say that is that this beam is made up of a whole sheet, a whole flux of photons. So that classical electromagnetic wave is a beam of photons. We haven't talked about quantizing the electromagnetic field yet. That will come at the end of the semester. But the idea is to say, however much energy this incoming wave is delivering, it's coming in a distribution of individual packets, individual photons. So however much energy is coming in the wave is equal to h bar omega, the energy of one photon times the number of photons. So one thing that's useful to do is to convert from the energy or the intensity of the beam into a number density of photons. And then we can talk about the transition rate per photon. That would be a beam independent quantity. So we're thinking about something along the lines of a rate dr d omega per photon, which would be a beam independent quantity. So how can I calculate the number density of photons? One way to do it is I can compare what is the energy being carried by the wave classically. So classically, that information is described by the pointing vector. The pointing vector is sometimes called S, and it is C over 4 pi cross product of the electric field and the magnetic field. The pointing vector describes the energy current. So that is energy per unit area per unit time. So something in units of joules per meter squared per second. So this, another way to say that is that this is the energy flux per unit time. So let's evaluate that. For our particular plane wave, we had E was minus omega over C A naught sine k dot r minus omega t. We had B was minus k cross A naught, also sine k dot r minus omega t. So if I calculate the pointing vector from this, S is C over 4 pi, E is minus omega over C A naught cross minus K cross A naught, and they both have the same sign, sine squared, K dot R minus omega t. So minus cancels the minus. I get A naught cross K cross A naught, and I can unfold that. So I end up with, let's see, omega over 4 pi K times A naught squared minus A naught times K dot A naught sine squared K dot R minus omega t. This is the back minus cap rule. In Coulomb gauge, however, this term was 0. So Coulomb gauge had divergence of the vector potential was 0, which translates to wave vector dot the vector potential is equal to 0. So we just get this piece. So what we get is that the pointing vector at any moment in time is omega over 4 pi K A naught squared sine squared K dot R minus omega t. So this thing oscillates back and forth as a function of time, but on average, if I take the average of this thing over time, then I'm just taking the average of sine squared, and that average is just a factor of 1/2. So what I end up with is omega over 8 pi times the wave vector k. And if I look at the magnitude of this thing, the magnitude of the pointing vector is times a0 squared. So the magnitude is omega k over 8 pi, a0 squared, and since omega and k are related, I can write this as omega squared over 8 pi c, a0 squared, and then it's going in some particular direction. Okay, so this is the typical energy per unit area per unit time, which is coming in from the beam. I can convert that to a number density or a number current of photons. So divide by photon energy. To get number of photons per unit area per unit time. So you might call this the current density. Suggestively, you might call it J. Magnitude of the pointing vector divided by h bar omega. And if I divide this out, I get omega over 8 pi h bar c a0 squared. So now let's go back to the answer that we derived for the transition rate density and normalize it per unit photon current. Per unit current density. So that is my transition rate per unit omega, and I'm going to divide it by the incoming current of photons. This object is called the cross-section, the differential cross-section. It has units of area. Because my rate has units of number per unit time, so this is 1 over seconds divided by angle, which is dimensions. And this 1 over the current, the 1 over the current is number per unit area per unit time. So 1 over seconds cancels 1 over seconds, and I get something with units of area. That's why this is called a cross-section. Since we've calculated the incident current, we get d sigma d omega is 8 pi h bar c over omega a0 squared times the rate per unit solid angle. And you can also write the same thing, differential in all 3 components of the momentum if you want. The important thing is this conversion factor from the incoming flux or the incoming current. All right, so when I plug this back in, I get the cross-section per unit solid angle is 32 e squared or radius cubed over m c omega h bar cubed. I have p final cubed cosine squared theta h bar squared plus p final squared or radius squared, h bar squared to the fourth. So overall, that is h bar to the fifth upstairs, 32 e squared or radius squared, and c omega, yes. All right, so this expression for the cross section we see has canceled out all of the beam properties. So this transition rate per unit current in is a property of the target alone. So this is referred to as a differential cross section. And the cross section is the elementary ingredient, the elementary observable that we calculate in scattering theory. Another thing that you can calculate related to this is the total cross section or the total rate. So the total transition rate is what you would get if you took that differential rate per unit momentum and you fully integrated it over all momentum. That's the total number of transitions per second. That's of course the same thing as integrating the rate per unit solid angle over all solid angles. And the same thing is true of the total cross section. So your sigma total cross section, is the integral of the differential cross section. And this is related to the total rate. Let's say this is my total rate. This is just 1 over the incoming current times the total rate. So if I calculate the integral, all I really have to integrate is the cosine squared beta. If I integrate, the total rate that I get is 16 over 3 e squared or radius cubed over mc squared h bar to the fourth, a naught squared p final cubed h bar squared plus p final squared or radius squared h bar squared to the fourth. And if I divide by the current, the total cross section that I get is 128 pi over 3 e squared or radius cubed over mc omega h bar cubed e final cubed times h bar squared plus p final squared or radius squared h bar squared. Okay, so we defined the thing, we calculated it. What does it really mean? A useful way to interpret the cross section. If cross section is, let's say, sigma total is the total rate divided by the current that's incoming. That's equivalent if you cancel out time. If everything is constant in time, then this is the total probability to scatter at all, divided by the flux, which is coming in. So a useful way to convert this is you can compare the same cross-section if the absorption probability was 100%. That's referred to as a black disk. If the target were a black disk, meaning probability is 100% to scatter, what area would it have? So if that cross-section were interpreted as the total probability of 1 on a black disk divided by 1 over the area, area of the black disk. That's another way of interpreting what the cross-section is. That cross-section is the area of the black disk that would have the same scattering probability. So for example, suppose you did the calculation and you came out with sigma total is 10 to the minus 28 meters squared. Then that means that if you had a uniform flux coming in, uniform distribution of photons coming in, that my target could be represented as a perfect black disk whose area A is 10 to the minus 28 meters squared. And this black disk would mean that photons which are outside of that area would just miss it, and anything which comes in inside that area would be guaranteed to be scattered. Right, so I guess in this case, it's the electron. So the cross-section is the effective area, the effective cross-sectional area that describes how much of the incoming flux the target is going to absorb from the scattering. The typical unit of cross-sections is 10 to the minus 28 meters. It's called the barn. We talked about that a little bit in the journal club yesterday. The term barn comes from the early days of nuclear physics during the Manhattan Project, when they were describing the scattering cross-sections or the scattering probabilities of neutrons that could initiate nuclear fission. And they described it as hitting the broadside of a barn with a tiny neutron and hitting a gigantic uranium nucleus. So this phrase comes from, you couldn't hit the broadside of the barn because your aim is so bad. And that has now become the standard unit for describing cross-sections in high-energy nuclear and particle physics. Okay, that is what a cross-section is. So this approach is essentially the foundation of scattering theory. This photoelectric effect is effectively describing that flux of photons coming in and how that photon strikes the hydrogen atom and ejects out of it the electron. And we get, at the end of the day, a rate per unit momentum, or we can get a cross-section per unit momentum. And so the name of the game in scattering theory is to do the same kind of exercise for some incoming projectile interacting with some potential and calculate the scattering cross-section for that event. All right, we've only got about 10, 15 minutes left, so I want to at least give you a flavor of what the scattering theory calculation looks like. Any questions on this? Essentially, all of the hard work for the photoelectric effect was done last class. The real discussion today was about what do you mean when you have a scattering rate like this? How do you think about it in terms of a cross-section? So I wanted to convey to you what a cross-section is so that you know what the heck you're calculating in scattering theory. Okay. So the basic approach in scattering theory. We will do all of this in more detail next week, but the basic approach is as follows. A couple of caveats for what I'm going to lay out here. So all of this is valid for the case of elastic scattering. Meaning no kinetic energy is converted into potential energy or into mass. You don't break the target apart. You don't excite it to an excited state. Kinetic energy coming in equals kinetic energy going out. Not only that, we're assuming a heavy target so that it does not recoil. So the idea is I have some particle which is coming in some momentum eigenstate, P initial. This thing is going to interact with some kind of potential, V of R. And then afterwards, after interacting with this potential, starting from T equals minus infinity, evolving to T equals plus infinity, we're going to end up in a final momentum eigenstate PI. So the elastic scattering assumption means that I can say the kinetic energy that I started with equals the kinetic energy that I ended with. The heavy target assumption means that I don't have to worry about this guy recoiling and absorbing some of that kinetic energy. Then I can very easily say that the energy of this plane wave equals the energy of that plane wave. So this is good for an electron hitting an atom or something like this. Not so good for collisions of targets with comparable mass. And the other assumption that will make it easy to write down the form of the answer based on what we just did is that we will work the lowest order in perturbation theory, which is, say, first order in perturbation theory. In the context of scattering theory, this is known as the Born approximation. But it basically just means that we can use Fermi's golden rule the same way we did before, sometimes also called the Born-Oppenheimer approximation. Okay. So we will set up this process exactly the way that we did for the photoelectric effect, which is using Fermi's golden rule. So we will say the transition rate per unit final state momentum is equal to 2 pi over h bar. We have a transition matrix element to the final state, TF, as a result of the potential, V, some operator V, from an initial state, which is also a momentum state, P initial. And then I have an energy conserving delta function, E final minus P initial. So a couple of words about this. Fermi's golden rule, we've usually been using it for time-dependent perturbation theory, where we had a perturbation of the form e to the minus I omega t. And then we had a minus h bar omega inside this delta function. What we're writing here is the time-independent case. Omega equals 0, so E final is equal to E initial. So that's, again, a little bit counterintuitive, but you can see from the setup of this problem that this is actually a time-independent problem. So that's different from what we had in the photoelectric effect. In the photoelectric effect, we had a particle that started here in the target and was subject to a time-dependent potential that caused it to get ejected. Now we have an incoming particle as a plane wave interacting with a time-independent potential, which is only a function of space, and then it gets ejected as a result. But the same essential procedure will work for us. Any questions about the setup? Once we have this, we can basically carry through the same steps we did before, and it's even easier. Okay, so under these assumptions, all of these assumptions are designed to allow us to simplify that energy-conserving delta function. If final kinetic energy is equal to the initial kinetic energy and they're all carried just by P initial and P final, nothing happens to the target, then this is just a delta function of P final squared over 2m minus P initial squared over 2m. And if I use the properties of the delta function, then this is m over P final, delta function of P final minus P initial, exactly like you would expect. So however much magnitude of momentum comes in is the same magnitude of momentum that goes out, but it can deflect an angle. The other thing that we can use is that we know that these are plane wave states. So that makes the evaluation of this matrix element pretty straightforward. P final, some scattering potential, P initial. If I write this in a position basis, I insert a complete set of position states. I get integral d3r. The normalization is 1 over 2 pi h bar cubed. This one came 1 over 2 pi h bar to the 3 halves. This one had it too. So together it's 1 over 2 pi h bar cubed. I have e to the minus I over h bar p final dot r. B of r e to the plus I over h bar p initial dot r. So I pull out some constants, 1 over 2 pi h bar cubed, and I get integral d3r e to the minus I over h bar p final minus p initial dot r times the potential, B of r. We've discussed this kind of integral several times now. What is this integral doing to the potential?
Fourier transform?
It's a Fourier transform of the potential. So this is going from V of R to its Fourier decomposition V of Q. And this is resolving the momentum modes inside the target. So another diagram that I can draw to represent the scattering process is to say I had an incoming particle, P initial. My potential had some spatial distribution, V of R. But what the scattering is doing is it's resolving it into all of its different modes, V of Q, where Q is a momentum scale. And then the particle goes out after having absorbed some momentum from that. So another way to represent this is to say I had a particle coming in with momentum P initial. It interacts exactly once with the potential at first order in perturbation theory. So I'll draw a zigzag line and a cross describing the insertion of the potential. So this is my V, and momentum H bar Q is coming in from the potential. And the particle that's going out has momentum P final, which is P initial plus H bar Q. So this is another way of saying Q is P final minus P initial over H bar. And that's exactly what this Fourier transform is giving. So your picture of scattering theory is at first order in perturbation theory, where I have exactly one coupling to the potential. This is the Born approximation. First order in perturbation theory, and it means that you pick up one momentum mode absorbed from targets. So that's what this process is giving me. Okay. So when I plug all of this in, I get my rate per unit momentum density is 2 pi over h bar. I have to take this expression and square it. So I have a whole bunch of factors of 2 pi h bar here. So I have 1 over 2 pi h bar cubed. And then I have the absolute value squared of that Fourier transform. D3R e to the minus I q dot r v of r squared times from my energy conserving delta function, I have m over p final delta function p final minus p initial. All right. And the last ingredient that I need is the incoming current to convert this to a cross section. Normalized by the incoming or beam current density. So that current density is the current density in quantum mechanics. The current density is IH bar over 2m minus IH bar over 2m. Psi star gradient of psi minus psi gradient of psi star. So if I plug in the incoming plane wave state, psi incoming of R is the projection onto position R of that initial momentum eigenstate. This is 1 over 2 pi h bar to the 3 halves, e to the plus I over h bar p initial dot R. So if I plug this in, I take the gradient. What I get at the end of the day is incident current is 1 over 2 pi h bar cubed, p initial divided by the mass. So this is a normalization constant telling you the number density per unit phase space. This is just the velocity, momentum divided by mass. So when I put it all together, I get the scattering cross section for an arbitrary potential. So d sigma d omega, d sigma d3 pf, I guess, is we have 2 pi h bar cubed m divided by p initial times the rest of these factors. So I have 2 pi over h bar, 1 over 2 pi h bar cubed. I have m over p final times the Fourier transform v of r squared momentum conserving delta function, p final minus p initial, 3 pf. All right, so as intended, the factors from the normalization of the beam cancel out. P initial and p final are the same thing. So I get m squared over p final squared. I have 2 pi over h bar integral d3r e to the minus I q dot r v of r squared times momentum conserving delta function Okay, and last but not least, we integrate over. Last, we integrate over the delta function, so I write d sigma d3 p final squared is 1 over p final squared d sigma d omega. So d sigma d omega dp final. I integrate over that magnitude. This is integral dp final, p final squared, d sigma d3 p final. So I take this expression, I multiply by p final squared, that nicely cancels this factor. The integral picks up the delta function, and I get d sigma d omega is, according to what I have here, 2 pi m squared over h bar Fourier transform of the potential. Squared. And where did I lose a factor of h bar or a factor of 2 pi? All right, we are over time, so I need to go ahead and stop here. I fumbled a factor of 2 pi here. So I need to go back and double check this. I will go through this more carefully on Monday. The final bottom line, the important thing here is that it's proportional to the Fourier transform of the potential. So the final answer with all of the correct factors is d sigma d omega is absolute value m over 2 pi h bar squared integral d3r e to the minus I q dot r v of q dot r squared. This object here is called the scattering axis. Okay, apologies for rushing through this. I fumbled something in the prefactors here. This is what I'm supposed to get. I've got the mass in the right place. Got the wrong number of 2 pi's and h bars though, so I've got to go back and fix that. With this setup in hand, you can calculate the scattering cross-section for any potential. So we can work out an example of this on Monday. Again, apologies for rushing at the end here. Any questions?
I have a question on the homework, but it can wait until everyone is done.
Okay, sure. If you want, you can just jump to my personal office, the personal Zoom room, and we can discuss there.
Would you be on the Zoom room right now?
Yeah, as soon as I clean off the board here, I'll go upstairs and I'll log in.
Okay.
All right, thank you. Any other questions? Okay, thank you guys very much for your patience. I'll get all these factors fixed for next time.
On the second thought, Professor,
Yes,
it's just a really short question, if you don't mind answering it right now.
Yeah, sure. Go ahead.
It's for homework 7, where we have the Zeeman effect on the fine structure states. So in class, what we did was H0 was the Coulomb interaction.
That's right.
So for problem 2, do we have to take H0 to be the fine structure interaction?
Yeah, so H0 is the Coulomb interaction and the fine structure interaction. You don't need to actually use the form of that Hamiltonian, but you do need to use the fact that its eigenstates are the ones of total angular momentum J because of the L dot S coupling in the fine structure.
Okay. Yeah, that's all I needed to know.
Okay, sure, no problem.
Thank you.
You're welcome.